Space Research Organization. He is a recipient of SN Ghosh Young Scientist Award in 2009, and he is very closely associated with Breakthrough Science Society, Kerala chapter. And he is also a part of, almost a part of Breakthrough Science Society. And he is involved in many science popularization activities, including free courses on advanced topics in the physics and quantum mechanics. So, on behalf of Kerala State Science and Technology Museum and Breakthrough Science Society Trivandrum chapter, I welcome all of you to this program. I now request Dr. Umesh Khatane to start his presentation. Thank you.
Thank you, Professor Rajan. I really feel little every time he introduces me because I am here with all of you. I'm sure most of you we have interacted in several programs. It is really nice to be involved in programs like this, and for the young students, this kind of culture of scientists or whoever working in sciences of branches of sciences interact is something which has made the Western society so enriched with technology and knowledge. Unfortunately, which is lacking in our cities, and this needs to be actively encouraged. And the audience here, there are accomplished scientists and technocrats. You should actually interact with them also. So, coming to this talk today, it's about bringing quantum phenomena to the macro scale. You know, every time I study or read about quantum mechanics, there is something which I remember from my teacher. Something which was said by my teacher. I consider Mirza Ghalib as one of my close associated teachers. So he said once, "आते हैं रैब से ये मज़ामी ख्याल में, गालिब सरीर खामा नवाए सरोश में." Means that the abstract thoughts come to my mind, just the gush of wind in the morning. The sound of my writing implement are the footsteps of revolution. Quantum theory was such a revolution in human mind, or ability of human mind, and we will experience that in today's talk. I have kept slides to bare minimum, only 20, and in fact I would like to cut them even shorter. Because the discussion today is going to be more about the philosophy rather than the science and the technology. And for the science, as Professor Rajivan indicated, very soon we will be having our Saturday course every Saturday or Sunday, depending upon how the my remaining realizable assets, etc., to be distributed annually as a prize to those who, during the preceding year, have conferred the greatest benefits to humankind. The interest is to be divided into 5 equal parts and distributed as follows. One part to the person who made the most important discovery or invention in the field of physics. One part for the person who made the most important chemical discovery or improvement. You see, his words were chosen very carefully. It's not simply, we'll give a Nobel Prize in physics and chemistry. Okay? What he's saying is something one needs to reflect upon. Okay? Then he comes to the next one. One part to the person who made the most important discovery within the domain of physiology and medicine. He didn't say biology, he said physiology and medicine. Okay? One part to the person who, in the field of literature, produced the most important, outstanding work in an ideal direction. Okay? Again, he has chosen his words very carefully. Okay? And finally, one part to the person who has done the most or the best to advance fellowship among nations, the abolition or reduction of standing armies, and the establishment and promotion of peace progress congresses. Okay? Now you see, it's very, very important to understand why he chose only these five. I mean, people joke about mathematics, okay? But for that, one needs to really see his pragmatism about how the effects of scientific research or any other intellectual activity should directly benefit humankind at large, not individual groups or individual people, set of people following a certain stream. It is my express wish that the awarding the prize, when awarding the prize, no consideration be given to nationality, but the prize be awarded to the worthiest person, whether or not they are Scandinavian. Okay, that just shows his thought process. Now, what is important to keep in mind is the first bolded part in this paragraph, distributed annually as a prize to those who, during the preceding year, have conferred the greatest benefits to humankind. And again, for my young friends here, you see, he believes, as a scientist, he believed that literature is something which is one of the most important aspects of human mind, which needs nurturing and it needs growth. And that's why he included a Nobel Prize not in mathematics, but in literature. Okay? So please read literature in your own language. Okay, so now let's come to quantum mechanics. Okay, I'm going to make statements which, if my physicist colleagues were here, would perhaps crucify me for, but please take them with a bit of salt. Just today morning, I got a message from my head of department saying that why don't you give the same talk in IST? I wouldn't dare to. I will modify it and give. But let me give you some idea, because I know I need to attract. This is more like an advertisement for quantum mechanics than quantum mechanics itself. Okay? So what's the fundamental difference between quantum mechanics and classical mechanics? Okay? There are many differences. Okay? And when you go to fundamentals, there are fundamental differences, but I am not going to bring them out here. As a common man, the way I look at it, the most fundamental difference between quantum mechanics and classical mechanics, what makes quantum mechanics superior, is what I am trying to show in this picture. I don't know how many of you can recognize the left-hand side picture. This is from a myth called Vikram and Vedal. It's basically a ghost which has to be carried on the shoulders of that king. Okay? So in classical mechanics, a physical system is that king, and the properties are the ghosts which is sitting on that. Okay? So the physical properties of a system are attributes which are external to the physical system. Okay? So when I go and shout at my students, I can always blame that I am under stress, I have some psychological problem or something. But finally, I am what I am. Now that is where comes the right hand side picture. No, the physical system and the physical properties are not different. Okay? The physical properties define the physical system. And this is something, a very important idea, an important paradigm which came after a lot of deliberation in the early decades of 20th century. And that is the biggest gift of quantum mechanics to mankind. the way to look at the world, not as made from the system, but the system itself. It has many implications philosophically as well as scientifically. We'll stick to scientific effects here. So basically, quantum mechanics says a physical system is not an external object over which physical properties are superposed, but rather the properties themselves are the physical system. Now, what it implies is something very, very powerful to even our perception of existence. So that's why the quantum view is far more abstract, much more powerful idea with radical implications to our sense of reality. Okay, if you spend a few years as a professional in physics, you actually start looking reality in a very, very different way than what it appears day to day. I really wish I could tell you more about it, but it is not something which can be told. It has to be felt. So that's what one very ancient poet said, "Dikha baat agam ki, kahan sunan ki nahi. Jo jane so kahe nahi, jo kahe so jane nahi." Means those who can tell you, they don't know it, and those who know, they cannot tell it. You really need to experience it. So you really need to marinate yourself with the idea of quantum mechanics. You have to take, for students particularly, you have to take minimum 3 courses on quantum mechanics. And not once a year. It's like breakfast, lunch, dinner. You eat one, wait, digest, learn other topics in physics and engineering, course, learn, experience, absorb, apply, take the third course. Then only you really start seeing these effects. So I'll try in this slide, try to just highlight few of them. And they are fundamental to quantum mechanics. What quantum mechanics or quantum theory brings to us? First, it brings something which is very popular. Okay, it's called wave matter duality. Unfortunately, it gives a very, very wrong impression to the students up to class 12 and sometimes even up to BSc. It takes a couple of more years to wash it off and reconstruct it, but okay, but it's a fact. Okay, so it is called wave matter duality. It is rather abstractness of existence. Okay, the way we perceive a physical system is by localizing it and then interacting with it. Okay, and fundamentally, even before quantum mechanics, physics actually built theories where you have a physical system and you had means of interaction. Okay, like I'm speaking, all of you can hear. That's a wave, and you people are sitting there. You are particles. I am speaking here. I am a particle. This mic is here. It's a particle or a matter particle. Okay? Quantum mechanics dissolves these boundaries. Quantum mechanics, the first step in quantum mechanics, where it actually people start thinking about quantum mechanics, is where people started getting confused. Because when we started going to microscopic scales, and that is the main topic today, microscopic scales, in the end of 19th century, people started getting effects which could not be explained either by pure particle picture or by pure wave picture. Things started getting mixed up. And then by 1920s, the wisdom emerged that no, there is no point in calling particles or something as waves. There is no difference between them. They are both waves and particles. You are, and it's not philosophy, it's physics. You are also a wave, I am also a wave. Can be projected as a wave. And that is where I said that it's a physical system is not just a physical system with properties, the properties themselves. Okay, so coming back to wave matter duality. So it's a very famous principle, it's called de Broglie hypothesis, which says that for every particle of mass m moving with momentum m has associated matter wave for lambda, and the formula is very simple, lambda is equal to h by t. Those who have taken basic course in +2, they know this. Okay. Now, this has more serious implications than simply saying wave matter duality, and I try to highlight that very soon. Next, something which physics was waiting for decades, and that is energy. Because as early as 16th, 17th century, people started doing basic spectroscopy. By 17th and 18th century, we started seeing that there are some things called waves, colors, wavelengths, and there are different colors and they are characteristic to different objects and so on. Okay, but we did not understand why nature or matter actually emits light in this kind of discrete lines. For example, the most famous one are called the Fraunhofer lines, which were observed in the solar spectrum. These lines, there was no obvious reason why they should be. You take particular type of salt, hold it in a gas flame, and you can see that the color of the flame changes. We didn't know why. And for that, we were waiting for very long time, and quantum mechanics gave us the theory of quantization. It told that the energy, electromagnetic energy, can travel only in packets of energy. That was Planck's law, E is equal to h nu. At the bottom it is written. But not only that, it also told that a system which is confined to finite dimensions will always have energy quantization. Any physical system which is confined to finite size will have specific energy levels, quantized energy levels. And whenever the system changes the energy level, there is going to be exchange of energy and light, or most of the time light is emitted, most of the time, not always. But not what is not very commonly known, but it is of course taught to our students at the UG and a PG level normally, is there is something called angular momentum quantization. Angular momentum quantization meaning when this fan is on, this fan is rotating, it has angular momentum. I can have this fan rotate at any speed. Suppose the power goes off, the fan will slowly come down to zero. It will pass through a continuous reduction in the rotational frequency. No, it doesn't. It actually goes through like this. And each of these steps is in packets of h cross, Planck's constant divided by 2 time. And this is so universal that every time my heart is pumping blood in the valves, there is a flow of blood, there is a small flow, rotating flow of blood. Even that is quantized. Only thing is, this step size, as we will discuss later, is so small that it is impossible on a day-to-day basis to see this, the fan to go in one rotation speed, then another rotation speed, then another. You will perceive it as if it is slowly going down. Okay? It is not. Whether it is a small nucleus, atom, molecule, red blood cell, a human, a fan, the earth, the galaxy, every object has quantized angular momentum and there is no exception to it. There is absolutely no exception to it in this universe. And that is something which doesn't come from classical mechanics, it only comes from quantum mechanics. Relevant for today, quantum theory also proves that the magnetic flux, the total number of magnetic field lines passing through a given area is also quantized. There is a minimum with which it can be added, and that is written on the bottom, phi 0, which is again Planck's constant divided by 2 times the charge of the particle. Then the famous uncertainty relation, but I will not discuss about that. It basically is important. If some other day when I give a talk, I perhaps would spend more time on it, but uncertainty principle shows that you cannot observe a system without disturbing it. Rather, it goes one step further. It says a system which is not observed is different than the system which is observed. It's very hard for us to digest such ideas, but that's why I said it requires marination. You have to really get marinated in that idea for some time to really appreciate. But yes, if you keep a boiled egg inside the box, keep it in the fridge, its quantum state when it was closed in the box, and when somebody installs a camera inside and look at it, it is different quantum state. And it's not philosophy again, this is science. Measurable, demonstrable science. Okay. Superposition. The famous Schrodinger cat problem. The cat is simultaneously dead and alive. Something again, goes against common sense. Entanglement, something even more radical. Okay? Imagine I lifting my right hand here and an entangled system in Japan, okay, lifting the right hand because we are entangled. Okay, this is something which has been demonstrated, not only demonstrated, it is now being used for quantum information processing. Okay, these ideas don't come from classical mechanics. You require an abstract idea of quantum mechanics only to understand and implement and convert them into technology today. Finally, particles as disturbance in field. This is a next level of quantum mechanics. It's called relativistic quantum mechanics, or something which goes through second quantization, where we say that what you call as particles, they are not particles, they are actually quantum states. For example, when you study atom, you say this is an atom and it has energy levels, right? Atom itself is the state. Okay. I wish I could spend more time on this, but it's a fantastic idea. It just proves that you are a disturbance in a field. You meaning a human, a system, this desk, they are disturbances in a field of some type. Okay? These ideas are crazy, they sound absolutely illogical, but I can assure you there is nothing more logical than these ideas when it comes down to systematic scientific mathematics. It's a pity that I cannot tell it to you today here. Then comes the quantum mechanics and the microscopic world. And this was a problem where humans started learning about quantum mechanics. And I will not get into the history of that, but I'll just simply tell you there's only one culprit which actually has made our life so difficult, is that first number there. It's called the Planck's constant. Look at the number. The number is so small, and that number makes everything which is related to quantization. If you would have noticed at the bottom, everywhere there is h, and everywhere there is h in the numerator. Okay, making everything quantized to very, 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 very tiny bits. And since these are very tiny quantized bits, their change in day-to-day world is almost impossible to perceive. I say almost with a very good reason. Okay, then it makes scales too small, photon energy, angular momentum, I just described to you. And then comes distinguishability of a measurement and a system. Okay? For example, and I always give this example, and I'll just stop at that example and I'll move to the next slide. Imagine you are entering into a very tall building. You want to go to, say, 12th floor. You press the button near the elevator. The elevator says it is at 7th floor and coming down. How does that display know that? It's very simple. The lift is a very big object. Every floor there will be sensors. It can detect the presence of the lift, say magnetic sensor, or you can have light in one side of the wall and the detector on the other side, and when inside the lift shaft, when the lift is moving up and down, this light will be obstructed. I will get a signal that the lift is there. Okay? So that tells me where the lift is. Where does the arrow come from? You just find out where the lift was, whether it was on 8th floor or it was on the 6th floor. If it was on the 6th floor, it is going up. If it was on the 8th floor, it is going down. Now, it's very simple. This happens every day. But a very important idea here is that you need to interact with the lift body to know where the lift is and where it is going. But then you say, come on, it's just light. I'm just obstructing the light. That shouldn't do anything to the lift. Yes, because compared to the momentum of the lift, the momentum of the light is nothing. Right? That is that h nu and so on. That makes life very, very difficult at very small scale. But suppose that lift is now reduced to smaller and smaller and smaller size, and then at some lengths or some length scales, the momentum of this lift will become comparable to the photon momentum. And then, if the lift is observed at a particular floor, okay, it will not be coming down or up. It may actually move horizontally out, okay, because you observed it. These ideas may sound very strange, but if one does a systematic study, we discover some very interesting behavior. But unfortunately, these effects are happening at small scale, or they become detectable at small. They are happening even at our scale, but they become detectable only at the small scale. And that is where physics was stuck for a very, very long time. Okay? Because finally, I need to build an enormously expensive, very specialized lab to build a device which will show me a quantum effect. Not just show me, there are many devices which are showing quantum effects. Okay? But even a mobile phone, the circuitry used in mobile phone uses quantum mechanics fundamentally. But can I use it as a tool to study quantum mechanical properties? No. You can use it to make a phone call. You can use it as a source of light. The LED is a quantum device, fundamentally. But there is no control. There is no input and output where you can actually study the properties at a quantum level. That you cannot do. Okay? So, this is something very important to appreciate when we appreciate the work of these three gentlemen who got Nobel Prizes. Okay? Now, the ideas of quantum mechanics are very interestingly known 200 years before quantum mechanics. Okay, it started with Fourier, Lagrange, Hamilton, Hilbert. All these people had already developed and there are many more, had developed all the necessary mathematical tools for quantum mechanics. What was missing was the ability to go to the scale where the quantum effects become discernible experimentally. We live on quantum mechanics, but that cannot be used to study quantum mechanics. You needed a mechanism to study quantum mechanics. And that was not possible till comes the next wave of physicists, Maxwell, Planck, de Broglie, Einstein, Niels Bohr, and then we start connecting the ideas which mathematicians actually already had listed, explored, developed mathematical tools for 200 years back. We started implementing them once we learned how to manipulate experimentally and do quantitative scientific study. And then once these ideas started coming in, there were some pockets where there were some gray areas, there were pockets where things were not clear, and that was made clear by the next generation of physicists, Heisenberg, Dirac, Schrödinger, Bohr, Fermi, Bose, etc. They built the physics around it. So we come to this year's Nobel Prize, to these three people. John Clarke was the professor, and Michel Devot was his PhD student, and Martinez was a postdoc. And they worked together, and they worked from 1970s. They were working on various ideas, but there was one fundamental motive behind their idea. The fundamental motive was how to build an electronic device or a setup or a gadget which I can simply realize on a macroscopic scale, manipulate it at a quantum mechanical level. Now you see, my hand moves with muscles. These muscles use quantum mechanics. Every chemical reaction is quantum mechanics. But can I control that quantum mechanics? I cannot. I can control my hand. I cannot control the quantum mechanics of that. Right? So I cannot take my hand to the lab and use it as a quantum device to study or implement quantum protocols. It's finally a classical system. It's going to pick up things. It's going to act on my command as long as I am alive or conscious. Right? That's all it can do. It cannot be used as a device to learn or implement or extract quantum protocols, quantum methodologies. For that, you require ultra low temperatures, you require ultra low sizes, you require specialized equipments, and that was a limitation. And in a few minutes, I will tell you why it means anything to common man. Okay? So when they did this work, okay, they devised a system, a device-based system, where they could actually realize quantum behavior, and not only realize quantum behavior, in the process they discovered something very fundamental, which is listed there, while applying the idea of macroscopic quantum tunneling was not discovered by them, this was already known. But they applied it to a macroscopic system, okay? And in that process, they discovered that in an electrical circuit, the energy you can exchange with that electrical circuit is also quantized. Okay? Again, the size of that quantum is so small, and I will come to that, that again, you can't see it in day-to-day life. If you simply build a bridge rectifier, you can't just vary the energy levels in steps. It will go continuously. It will appear continuous. But at a microscopic scale, it will appear in steps. So they needed to build a device. Okay? So, before we get into the details of that, let's look at the citation. This is from the Nobel website. I would not read the whole thing. I'm not a great fan of having a large number of statements on a slide, but I would like to highlight what's the big deal about it. So please read the bolded part. Offers new potential for experiments using phenomena that govern the microscopic world of particles. It can be regarded as a form of artificial atom on a large scale, an atom with cables and sockets. Okay, so this is the great advancement the research work of these three people have contributed to humanity. And let's go ahead and hear about it a bit. I will spend about 10 minutes, 15 minutes on that maximum. Okay, so this idea of their circuit was based on a much more fundamental idea which was proposed by Josephson in 1962, and for which he was given Nobel Prize in 1973. In 1962, he was just a PhD student. And the idea was very simple. Okay, it was concerning superconductors. Now, as we all know, superconductors are devices or it's a material in which current can flow with zero resistance. It is not approximately zero resistance. It is not very, very close to zero resistance. It is zero resistance. Period. Okay? This statement has serious implications in physics. Okay? It is not resistance coming down from ohms per meter to milliohms to microohms to nanoohms to picoohms to attoohms. No. It goes to microohms and then zero. And that is a phase, okay, in physics it is called a phase transition. It's a very specific type of phase transition. The very nature of electron changes, and that we are going to discuss. Okay? In that process, basically, what you get is a material, a wire, which is having zero resistance. So you do not require to do any work to maintain a current to flow. So if you take this wire and make a ring like this, okay, and somehow you set in a current into this ring, this current will never stop because it is doing no work. The energy is not consumed anywhere. So it will keep going like that. Okay? And of course, whenever you have currents flowing in a room, you produce magnetic field. So this magnetic field will be there permanently. So you can build permanent electromagnets. Now that's an oxymoron. You can't have a permanent electromagnet, but this is a permanent electromagnet. If you excite this electromagnet made from superconductors, then it will remain permanently magnetized unless you make it do some work. Meaning, if you take one metal rod and go close to this, don't do that, but close to this and you just move it around, it will induce currents in that metal. That metal is a normal conductor. So there will be consumption of energy, and that energy will be taken from the energy stored in your magnet, and so the magnetic field will reduce. Why I said don't do this is because such magnets are used in several day-to-day applications, including MRIs. Particularly MRI machines, you would have seen that once the patient is set into the machine, nobody is in that room, everybody is outside because the magnetic field levels are extremely strong, and I'm going to come to that in a minute. So, this is a superconductor. Why it becomes a superconductor, that we will discuss, but it is due to some fundamental change in the way electrons behave inside the solid. Now, I take this wire, superconducting wire, and I cut it. So the obvious logic is, if you cut it, the current should stop, because you have now cut it into two. But in 1962, Josephson demonstrated theoretically, and then later on it was proven experimentally, that if the gap in that cut is of the order of, say, 100 nanometers or so, the current doesn't stop. It tunnels. It goes through. Okay? It goes through because of something which is called Cooper pair. I told you about me and my entangled twin sitting somewhere in Japan. It is like that. These two fellows are sitting and they are still talking to each other. Okay? So the current can still flow. Okay? And this Josephson junction property, this is called the Josephson junction. If you take a superconductor, cut it into two and put a gap in between as an insulator, that insulator can simply be air, okay? Air is a good insulator. Or it can be some ceramic material or something. So it becomes an insulator. So you can demonstrate that the current doesn't stop, it goes through. That was discovered in 1962. Then in 1964, somebody made, instead of making one wire, superconducting wire having a gap, they took loop like this. Meaning, one superconducting wire which is connected like this, another superconducting wire which is connected like this, and brought them into two junctions. Okay? This device is called superconducting quantum interference device, or short form SQUID. Okay? And this SQUID was the foundational device for their research of this year's Nobel laureates. Okay? And in 1973, he was given Nobel. So this is what happens inside a superconductor. On the leftmost side, what you have is those gray dots are the atoms in the metal, the atoms, and the orange colored small balls which are running around, those are our electrons. And as they move around, for example, if a small kid is moving in this gathering, that kid of course will, hit many of you as it is passing around. Like that, the electron would also do the same. Okay? But as you reduce the temperature, something interesting happens. First, look at the leftmost picture. Look at those gray balls. They are not properly ordered. They are not properly organized. Because of the temperature, because of room temperature, those atoms are also moving from their position. Very slightly, but they do move. They are getting disturbed from their mean position. But as you reduce the temperature, look at the middle picture. They are getting more organized. Once they start getting more organized, their response to the movement of electrons also becomes more organized. And you get something very interesting which is happening in the middle. You can see one electron moving in the center. Okay? As the electron moves, it causes a small disturbance in this crystal structure, and the second electron gets attracted towards it. Okay? Because it's a positively charged wake. Okay? We can discuss what this means. And then, below this critical temperature, these two electrons understand that we can live together and move together very easily through the crystal if we remain in the wake of each other. Okay? And this is something which is followed by birds also. I don't know if you have seen the birds, they normally fly in a V formation in the evenings and the mornings, you will see. And what you will, if you have enough time, please watch them. You will see something very interesting. If they change their speed, the V angle changes. If they are going fast, this angle becomes small. If they are going slow, this angle becomes large. And if you have even more time, please watch. You will see that periodically the bird in the front moves back and another bird takes the lead. This is because the first bird produces the wake, and that wake makes flying for the other birds slightly easier and more energy efficient. But in that process, the first bird gets tired. So after some time, the first bird moves and another bird takes the lead. Okay? If they move fast, this cone angle changes, and that cone angle is tan inverse of the speed of these birds by the speed of this oscillation of the sound, and that's angle you can calculate, and actually you can see that it is moving, it is changing this angle as the speed changes. It's very nice. If you can measure the angle, you can find out the speed. If you know the speed, you can find out the angle. So this something similar happens, but it happens at a quantum mechanical level. There is something more which happens between these two electrons related to their spin, but I will not spend time on that. So they become a pair, and this pair is called a Cooper pair. This is called a Cooper pair behind this name behind a scientist who was one of the Nobel laureates who got Nobel Prize for discovering or explaining, not discovering, explaining high temperature superconductivity, this famous DCS theory. Okay. So this Cooper pairs, now imagine this is a pair of electrons going together everywhere without losing energy, and that's why it becomes a superconductor. Okay, so how a normal material becomes superconductor? These electrons pair up and then they start moving together without losing energy to anybody else. And this only can happen at a very low temperature. Every material has every type of superconductor has a critical temperature below which only it becomes a superconducting matter, and below which the Cooper pairs are formed. Now these Cooper pairs are basically siblings who are associated with each other but at a long distance. Okay, so if you take one with you, the other will follow, no matter what happens. Okay, and that is what happens here in this tunneling. So in here you have a Josephson junction. Left side you have a piece of superconductor. There is a insulator in between and another superconductor. And this joint you normally think will stop the current. It doesn't stop the current. It actually allows the current to go through. And because of the process called tunneling. And this was known before these three Nobel laureates started their work. Already the Nobel Prize was also awarded in this. Then what grade did they do? Okay, we'll come to that. Okay, now this has applications. So the question is, what are the applications? Okay, so if I have these two superconductors, if I apply no voltage, meaning to sustain a current through this, I don't need any voltage. Okay, a DC current will flow. But what if I apply voltage? If I apply voltage, due to some very interesting properties of these electronic wave functions, okay, something interesting starts happening. Electrons start getting confused. So sometimes they jump this side, sometimes they jump this side. Normally you apply DC voltage, you should get DC current. Here you get current without voltage, and if you apply DC voltage, you get AC current. Okay? And this AC current is something which is then used for many interesting purposes, and we'll come to that. Okay? Now, when you pass current in a loop, you produce magnetic field. Okay? That means there is some connection between current in a loop and magnetic field. Okay? So every time you subject this loop to a field line, magnetic field line, there is an effect on the current. Okay? Day-to-day life, this effect is not detectable. But if you make this kind of loop, which is called a squid, I told you like this. Okay? This loop will have an effect of this magnetic field, and that effect is in phase. It is called phase. In quantum mechanics, it's a phase. Okay? And that change in the phase causes change in this current, the current passing through this junction. Okay? And this can be measured. Again, details we can discuss, but what is so great about it is there are two great advantages of using this device. First, it is extremely sensitive. This change is detectable for extremely low magnetic fields, and I will show you some numbers. You will understand what I mean. Okay, so the first great thing about this device is the device is responsive to an extremely small amount of change. That is first thing. Second, something very, very important. You imagine you want to measure body temperature. You take a thermometer, your body temperature is, say, whatever, 30 something centigrade. It changes by 1 degree. You can measure. Very nice. Now you take another thermometer, you go to a factory where iron is being molten. The temperature there is, say, 1700 degrees centigrade. And the manufacturer says, I need to control the temperature there 1700 degrees centigrade plus minus zero point 0.1 degrees centigrade. Now that's a hard job. That's a very difficult job. You need a sensor which can give you a fidelity, a variation of 0.1 degrees centigrade at nearly 2000 degrees centigrade. Right? Imagine now I demand that I want to measure the temperature of the sun, the core temperature of the sun, which is 1,000,000 degrees centigrade, and I want the accuracy of 0.0001 degrees centigrade. Okay? Now this is 1 in 10 to the power 9. 1 in 10 to the power 9. Extremely hard to achieve. Squids can achieve magnetic field sensitivity of the order of 1 in 10 to the power 14. That is the simplest squid device. A space grade squid device launched by NASA has achieved, for gravitational measurements, has achieved 1 in 10 to the power 18. Okay? That means you go from one value of magnetic field and another value of magnetic field in 10 to the power 18 steps. That much it can measure. Okay? So these are extremely sensitive devices. I told you, once you try to apply voltage across this junction, the electrons get confused and they start jumping, and that jumping has a very specific frequency, and this is called, the frequency of jumping is called Josephson frequency, and it is related to the voltage you have applied, delta V, the voltage across the device, 2 times the electronic charge, delta V by H. You can see E is fundamental constant, H is fundamental constant. So this gives you a clear connection between voltage and frequency. Now what does it mean? We all know voltage is actually a potential difference. There is no absolute scale of voltage. Now I give you a multimeter and say measure the voltage across a battery. You say 1.2 volts. Another person measures it as 1.2, 1.3 volts. Who is right? Who is wrong? It could be multimeter is faulty. It could be the battery is charging or discharging. We don't know. There is an uncertainty. Now I need to know whether my voltage is correct or not. How to find out? I need an absolute natural scale. Okay? I wish I could tell you what this demands from physicists. A natural scale. You require a natural scale. This is a natural scale. Because you can count frequency. So now you can, instead of measuring voltage with a multimeter, you apply that voltage across a squid and measure the frequency produced. And frequency can be counted to very high accuracy today with electronics. So you can actually now have absolute scale for potential difference. Okay? And this is that number, F Josephson. At 1 microvolt, you get 483.6 megahertz. Actually, there are more digits after that, but okay, I'll save time today. It also shows that the magnetic flux is quantized, and this is the flux, quantized flux. This is the minimum size of the flux again. Okay? Right? So this is where we will now switch to the last part, where we'll quickly talk about few applications. Why Nobel Prize was given to this? For 2 reasons. First, to bring quantum mechanics at a macroscopic scale, because they actually built this RF device. And that RF device is not atomic scale. It is 1 centimeter by 1 centimeter, the device. And then the microwave feed, which is about this length. You can actually buy it. Bring an oscilloscope, bring an RF generator, and you can actually study quantum mechanics directly. And use it as a voltage standard to characterize other devices. This is the one of the applications of this technique. The other is something very radical. When our blood pumps through our body, it is moving. Fundamentally, hemoglobin is not ferromagnetic, even though it has a iron in it. It's not ferromagnetic. Okay. In fact, it is mildly diamagnetic. Oxidized blood is mildly diamagnetic. Okay. But these are, at the end of the day, these are spins, magnetic. They are tiny magnets. They are tiny magnets. So whenever the blood is moving in the veins, it actually produces magnetic. Okay? So the largest amount of blood pumping happens in the heart. So heart produces magnetic field of the order of 10 to the power minus 10 Tesla. Earth's magnetic field is 10 to the power minus 4 Tesla. Okay? So you can imagine now how weak the magnetic field of my heart is. But there is magnetic field produced in the brain also. Whenever the electrical signals are going through the neurons, that is also current. It produces magnetic field. And you see that magnetic field. It is 9 orders of magnitude weaker than the Earth's magnetic field. Okay? So if you can build a device which can actually measure this magnetic field, you can actually use it for medical diagnosis, okay, without disturbing the patient. Okay? So this device called SQUID, superconducting quantum interference device, is at present used. Even in India there are facilities where patients actually use this. In many technologies like magnetoencephalography, where there will be a crown on your head with a large helium cryostat, because these are superconducting devices, they need to be cooled to liquid helium temperatures. And the head will go in and it actually maps the magnetic field profile in our brain and identifies the locations. Now there is an ECG or EEG, electroencephalogram. Okay, there is MRI. Then what's the use of this technique? First of all, EEG has a very good temporal resolution. It tells you about, as a function of time, how your electrical signals are moving. But it doesn't tell you where exactly they are moving. You can't have, normally they put 5-6 electrodes. In special cases, they put many more electrodes. But everywhere you can't put electrodes. MRI tells you localized magnetic field as a space. But MRI takes so much time that it doesn't tell you how it is changing with time. Okay? But a SQUID scanner tells you in space and time both how the field is varying. But usually the resolution is worse than, the position resolution is not so good as MRI. So people normally combine MRI with magnetoencephalography together. Okay? Then there is something called magnetic field imaging. People actually image the magnetic field of liver to check if there is any damage or lesion in the liver. Any modification, it can be detected. So that is called magnetic field imaging. You can have magnetocardiography. You image your heart. Okay? Magnetospinography. In your spinal cord, there are fibers. If anywhere the fiber has a discontinuity, okay, it will, collection of such discontinuities leads to dementia. Dementia comes from such breaking of linkage. And by using SQUID, it's not future, it is being done. You can actually map the entire neural network and identify places where this disconnection has happened. There is no direct remedy for that, so dementia cannot be directly treated, but at least you can check for the early onset and give supportive medicine. Okay, but this is possible because of such devices. Okay, and I told you about the liver function and all that, so magnetogastrography also is done. These techniques are expensive right now. They will become cheaper and cheaper as the technology progresses, but they are already there in the market. You can actually buy scanners commercially for these applications, and there are medical experts trained in this technology. This year's Nobel Prize was given to these 3 people because, not just for this, because these are established applications, is because once such a device is available as a quantum model, a physical quantum model, it can be used for quantum magnetometry, and it has its own great applications. I am not getting into that. Okay, quantum magnetometry has fantastic applications, not just scanning the body. And quantum computing. Okay, today the biggest challenge for quantum computers is to have a quantum system on which you can do computation. Okay, and controlling it. And engineers always like to control things with electrical signals and with a nice computer interface so that you can actually instruct what to do, where to go, what to change, what not to change. Okay? Imagine you have an atom at ultra low temperature and have 5-6 lasers exciting and de-exciting it. You don't have much easy, it's not an easy control. We do control it, but it's not very easy. And electrical circuits is what these people build. Is so easy to implement, so easy to control, and today the only bottleneck is temperature. And that is also getting solved as we make more and more miniaturized cryocoolers. This will again become easier slowly. But these are techniques which can be made so common that you can actually buy a quantum device in a shop. It's possible. Okay, so that is why it has implications. These are just two last slides. I show you a photograph. This is magnetoencephalography. There was this, I forgot to add the graph here. Actually, this is MRI image superposed with magnetoencephalography, and the picture shows, and this is a paper, very nice example they have given, is where the pure imaging cannot tell you the fault, but the fluctuation in the magnetic field profile has identified an onset of a stroke. And this is something which these devices can do. It's a very, very nice device. Similarly, this is an example of magnetocardiography, where another scan is made by conventional means of a human heart, and then using the magnetic scanner, they could identify an exact location where the artery, this is the place where the nerves, the neurons, because you know that there is a ailment, there is a disorder called cardiac arrhythmia, because our heart uses it is an efficient design, so it uses the same set of valves for both type of bloods. But if there is they are synchronized, so that when oxygenated blood is going, then deoxygenated blood is blocked and so on. But this has to be done in a synchronized manner. If this synchronization is lost, which is called cardiac arrhythmia, then the person can die simply because the wrong type of blood is getting mixed. So this control is by a certain neurons which are sitting on the arteries, main arteries, and these neurons can sometimes backfire. And that's why when a newborn child is there, or in the child is 7 months in mother's womb, doctors are listening for that rhythm. It's very, very crucial, because the body has to set that rhythm correctly. If not, then it's very dangerous situation. So that is where people put pacemakers and control this. Okay, so this kind of thing can pinpoint where the neuron is actually damaged, or the place where the neuron is misfiring, and it is possible to, in principle, in some cases, people have actually been operated and that damage is corrected. I don't know how easy or difficult this is. I'm not from the field, but this is something which is definitely relevant to common people. So, unlike many Nobel Prizes in the past, I wish I could give a seminar on them with the same enthusiasm as I could give for this one, because in those cases, especially the just 2 years back, the attosecond physics Nobel Prize was given on purely speculative idea that it may lead to things. Unlike that, this Nobel Prize comes from a very long line of Nobel Prizes which have been given for the use of magnetic field for sensing, especially medical sensing, but in general sensing applications. NMR, 2D NMR, MRI, 3 Nobel Prizes given. Superconductivity, Joseph's invention, BCS theory, 3 Nobel Prizes given. Super. Okay, so I hope I have managed to sort of tell you the abstractness of quantum mechanics and how it has been brought down to day-to-day life at a macroscopic scale by these 3 Nobel laureates this year. Thank you.
Thank you so much for this wonderful session. So now we have a Q&A session. So if you have any questions.
questions.
So just a query. You told about that magnetic flux of brain is something like 10 to the power of minus 14 that level. Unit of circuit. But then my question is, when we do MRI, the magnetic field is going to be tremendously high. How this interaction will take place between the physical body of brain or the cells of brain or the neurons, and how does it really affect? People say that MRI is not a problem for human body. Just wanted a clarification.
It's excellent. The way the human body works is by molecular functionality. Okay, and the molecular functionality is totally unsusceptible to such magnetic fields. What the magnetic field which it is producing is it's like, okay, I wouldn't give a sort of metaphorical answer, I will give a scientific answer. So the magnetic field which we are talking about is rather not a DC value, but a fluctuation. And that fluctuation is because every nucleus or every red blood cell has these magnetic needles pointing in random direction. It is just that every RBC has many such needles, okay? And not all of them are the same. No two RBCs will have exact same orientations. So now if I have a small coil and my blood is going through that, one RBC goes, it induces a magnetic field. Another RBC goes, it will induce a different magnetic field. It has absolutely no effect on the functionality. Now, when you subject the patient with extremely strong magnetic field, what will happen is these needles will rearrange themselves magnetically. Okay? Now, in biology or in chemistry or in molecular physics, if the reaction has to happen, you have to change the energy of the system by certain minimum amount. The advantage and the disadvantage of magnetic energy is it is so tiny. The magnetic energy per unit volume is so small that this reorientation of needles inside the red blood cell will have effects much weaker than a virus simply coming and hitting the cells in the blood. So the biological and chemical functionality of humans will be at a molecular level unaffected. But there are effects. Okay? But those effects are effects which are accumulated over many months or years. So if somebody is subjected to strong magnetic fields for a very long time, there are possible effects. Okay? These are not necessarily these effects, but other effects. But an MRI scan is perfectly safe.
Yeah, thank you, Umesh, for a wonderful lecture. Just I want to have a clarification. Now, whatever matters you presented, does it imply a total, especially in the medical field, a total replacement of the word electron with a magneto kind of thing? Or is that the direct implication of this current Nobel Prize discovery, or is it regarding the precision with which it does the job?
So, especially when it comes to neural diagnostics, at present the neural diagnostics, the only non-intrusive neural diagnostics is every other you have to physically put electrodes. So, this is the one which observes things even deep inside the tissue. Because if I have to see the neural functionality on my heart, I need to put the electrode rather there. So in EEG, for example, this is inferred from by putting it from the other nerve centers, where these are the junction points or the traffic junctions of the electrical signals, and from that the data is inferred. Here you are actually looking at the functionality of that specific neuron. So this is an advantage it has. Whether it will totally replace, I don't know. I don't know whether it will ever totally replace. But definitely, this is a much safer and much easier technique. It's a passive technique. You don't inject anything. You don't send anything to it. In fact, that magnetic field in MRI is required for the nuclear speeds to orient those needles. This squid doesn't even need that. There is no external magnetic field applied. You just simply keep the device. So if we could get a squid on a watch, for example, then a large number of fine diagnostics can be done just by hand. Only problem is you can't have it at cryogenic temperatures here. So
See, nothing is externally embedded. It does not imply a large reduction in the power required to
yes, so right now the device looks very big, but the actual power consumption is very small because it is purely passive device. The size is large because of the helium circulation and cryostats. And the rest is only electrical interface to pick up the signal. So that is nanovolts and microvolts. Nanovolts, in fact, nanovolts or picovolts. Very, very fine. So it's very low power consumption.
So I had a note. So in special relativity, we learned that no information can travel faster than light, right? So does quantum entanglement violate that?
No, it doesn't.
So how does it not violate?
Yes. So the question is, this question often comes, and again, I am not the right person to answer that, but I'll just give you a very superficial answer. The definition of information, okay, is the state which you record there has to make a consistent logical sense. Simply, my dual sitting in Japan lifting right hand is not an information per se. It can be information locally, but it has nothing to do with me, right? Till there is a correlation between the two, right? So to convert this information, my state here also has to be propagated there, okay? And that is the problem, okay? And no means you follow, whatever means you follow, it will take speed of light. So fastest is speed of light. You cannot still. You can have effects, but you can't use them to transmit information faster than speed of light. But this is a very crude answer, okay? So this sir is the right person.
Professor Umesh, it was a very wonderful lecture. Thank you for that. My doubt is in this area, you were telling that when you put a DC over this, you will get an AC current which is of high frequency.
Yeah.
So what will happen if you give an AC current? And
Okay. The problem is when you start sending the AC currents, okay, AC voltage. Okay. There is a part which I didn't discuss. Maybe a little bit. I'll give a little bit extended answer. In quantum mechanics, localization. That's why it is of that size. Now, that whole object has that identity. So, this varies as a function of position. In a superconducting state, these electrons, their wave function, loses the relevance of space. There is only one factor which I in between mentioned called phase. Only phase survives. Okay? And this oscillation, what you see, is because the tunneling of electrons from one side to the other changes the phase here. That causes another shift in the voltage. Actually, this equation F Josephson is equal to some factor multiplied by difference in the phase at two sides. Okay, so that is switching. By putting AC voltage, you are adding that whatever was the change in the phase which was happening due to the tunneling. Over and above that, there will be change in a phase due to what you are sending. Okay, so I will give you only a philosophical analogy to it. It's not scientific. It is like I have a guitar string and I am playing it and it is making one particular note. and it is going, that signal is picked up by the mic and it is going through the speaker and everybody can hear that note. And to that I add another frequency electronically. So I will hear some complicated interference of the two. That's what you will get here. So the phase change on both sides is the natural frequency what is shown here. And then on top of it, you're changing the phase by external means. So it will be an interference of the two. So you will see, you will not see a very nice sine wave like this. If I haven't done the calculation, but in my understanding, it will look like beats. It will look like for some time there will be an increase in amplitude, then decrease, then increase, but inside there will be this high frequency. Assuming the outside voltage is varying very slowly. But this is my guess. One needs to do the mathematics. So that is this wave is actually a current wave, and this current wave will have an amplitude related to the area of this loop and the flux passing through it. It's like magnetic dipole moment is proportional to the area into current in the loop, right? So now you are varying the current, the magnetic dipole moment will change. Now here you are changing magnetic field, certain amount of current will flow. So that conversion has to be decided by the area of the loop.
Just wanted to, in the beginning you were talking about the distinction between classical physics and quantum physics as system and properties are external to the system in the sense, and in the other case the properties make the system.
Define the system.
Yeah. Now, how do you connect this to quantum information, or is it connected to quantum information?
It is.
Second
It
question I'll ask after.
Yeah, it is. In fact, the foundational theory of quantum mechanics, it is very clear that the process of measurement is part of the system, and no measurement can be accomplished without exchange of energy, and such change is information, and that's why information is energy, or information is exchange of energy. So any exchange of information will bound to involve a process of measurement or interaction, and every interaction will bound to involve exchange of energy. Then only information can be exchanged. So this is a very important requirement of quantum information.
The one small question also I'll ask, that the previous slide which was showing, whenever you write the equation connecting energy, in the case of the photon, you write E is equal to h.
Yeah.
But in these expressions where you had a q phi and things like that, it was always h by 2. Any reason? Both cases I noticed h by 2. Q phi naught and the q
Yeah. And sorry, I couldn't get so the question.
No, if it is photon, you don't have the 2. It is straight.
Okay. That's okay.
The other cases it is h.
The problem with this is slightly different. For example, actually in that photon case also, there comes 2. Okay. If you see the last line, which is in red, okay, photons are not the photons are not the particles actually. Photons are the states of the field. Okay, and the lowest state of the photon field is h nu by 2. So, but having said that, I think this factor of 2 is rather a natural. It's like why it should be Planck's constant, right? I mean, it need not be called as. If somebody else would have discovered, you would have called it by different name. But naturally this is a number and it has some dimensions. That's why it has come. So I don't think the reason of 2 is very naturally coming, a factor of 2. If somebody else would have discovered the phenomena of quantization using say magnetic field quantization, they would have given Planck's constant as a number which is h by t, and then the h nu photon would have had 2 in front of it, because these constants are universal constants, so they will go in different form.
If we can ask a third question. This is regarding the poetry which you quoted actually, since you were talking philosophy. I think it was in Hindi, but you called it ancient. Hindi is a medieval language, right?
Okay.
13th century, 15th century, 18th century.
Yes.
Suppose you say Tattwamasi, for example, that would be ancient.
Yeah. Okay.
Before the Buddha, 6th century.
To me, what ancient means could be very subjective. That is one thing. Second is the language or the part which I recited was something which is actually from 13th century. Okay. So perhaps I just categorize it as ancient.
Because the same sense is carried by Tattwamasi. That is 6th century, before 6th century.
Yes, I mean, these ideas.
Ancient medieval.
Yeah, I mean, the philosophy of this, the philosophy that a thought cannot be expressed in totality in the form of language or any other form of expression applies to all philosophical lineage. Confucius, everybody had thought, even Plato and all these people had thought of this. In some way or the other, they have expressed it. The beauty of mathematics is mathematics does not leave such subjectivities. No, that is the power of mathematics. Mathematics, to a very large extent, removes this need of language. It builds its own language. So that's the power of mathematics. That's why we use it in physics so much.
Last question. Hello, sir. Thank you for the lecture, sir. When we cool many atoms to a very low temperature, they start behaving as one big matter wave. That's what we see in Bose-Einstein condensing. So, does Cooper pair? Do Cooper pairs also share a similar property?
Yes and no. Okay. For example, the Bose-Einstein condensate which we have, this has a very specific superatom behavior, coherent behavior. Okay. Whereas Cooper pairs only ensure that the resistance has gone to 0. That doesn't mean all Cooper pairs are in an identical state or something. That is not required. Okay. The quantum state, finally we write it in the form of bosons, and then we write them. Actually, that's what I mentioned, that there's a square root of n times the phase factor. But this behavior is distinct in cold atoms and in Cooper pairs. And then there are other effects like Meissner effect and formation of vortices and all, which is not happening in case of cold atoms. So in that sense, the similarity is pure similarity, they are not identical.
Yes, sir, and one more question. Like in the Josephson junction, we see a quantum tunneling effect in the Cooper pairs. But that is a probabilistic effect, right? So not all Cooper pairs at a given time will pass through that junction. So doesn't that affect the accuracy of that squid system?
Good question. If I believe what you are asking, you know what you are asking. I am assuming that you are asking. These are called quantum fluctuations, and actually they themselves are a very interesting source for quantum information processing. That's called true random generation, random noise generation. So if you want a true random noise, then because the current will fluctuate in the mean value, that is because of this fluctuation in the number, square root of n. If n number of pairs are tunneling per second, then the error will be square root of n. That will be the fluctuation, and that actually can be treated as a true random number. And if you can read it, you can interface it to a computer and use it as a true random number generator for encryption.
This is the last question.
Hello.
Yeah, my question is sort of simple, in the sense that I don't intuitively feel quantum. I mean, I feel I'm living in a world which is non-quantum. Intuitively, once you said switch off the fan, I feel it's coming down gradually. I don't feel it's coming down in quantum, whatever. So the question is it that quantum events happen at certain, say, high temperature or very low temperature or certain extreme conditions, or they are happening in such a way that our senses are not able to detect it for some reason? I mean, what's going on? That's
I always give one example for this, and I really like that example. I take that bottle of water, and I have a tawa on which people make this paratha. So it's a of course dosa in the restaurant. It's a big tawa, which is at very high temperature. I pour this water. What do you think will happen? So the most obvious thing to expect is the water will start evaporating, right? Do you think it is possible that it will simply become a block of ice? Yeah, no, but actually it can happen. There is a small but finite possibility that that would happen. The problem is that the probability of that is so overwhelmingly low that you will not see this effect. But if you reduce the size of, and I am not talking about metaphors here, actual physics, you make this thermal system smaller and smaller and actually start sending 5 or 10 molecules of water, you actually can see this happening. If you reduce the number of possibilities, then extreme possibilities also start becoming possible. Now, you can say, okay, why should I care? In the day-to-day life, it doesn't matter to me. This mobile phone, for example, uses RF radiation, which is almost a gigahertz. Okay, once you have such a high frequency, even a tiny piece of wire left after soldering, if I forget to cut that small piece of wire, that thing will radiate energy because it's an antenna. Okay, so if I take a diode, a transistor or a diode, simple, and apply it to 1 gigahertz frequency, it will simply not work because of the scale. So these diodes have to be reduced to very small size. These are very famous diodes, Isaki diode or Schottky diodes. These are made extremely small. Physically, the die will look big, but the actual diode is less than a micron. Even the processor for this mobile phone uses nanometer scale technology. So there are tunneling effects. And not that these tunneling effects bother us in the design, we actually use them deliberately to operate these devices. So yes, at a microscopic scale, when I come to technology and engineering, I can see the effects of quantum mechanics and I can manipulate them for my usage. But do I feel them? No, I don't feel them if I go with a certain perception of the world. But the same world believed that if I take a stone and throw it in air, and if the resistance is made 0, even then it will slow down and stop. Even today, if you ask a person who has not been exposed to the complete chronology and the scientific training of Newton's laws, will firmly believe in that. If you ask that person, you throw the stone, will it stop somewhere? It will go and stop there. What if you throw it in space? It will stop somewhere. Right? So, unfortunately, we live in a world of perception. And our perceptions are built on the basis of what we sort of take for granted. And that is where science becomes very, very crucial. It teaches us that we should learn to slowly, not abruptly, disconnect yourself from these perceptions. Somewhere we have to disconnect the perception, okay, and come down to scientifically falsifiable and verifiable numbers. So To my eye, the fan will appear slowing down continuously, but my persistence of vision is 10 milliseconds, 100 milliseconds, right? Even a mobile phone, when I'm or laptop, I see a movie. It appears a continuous movie, but it is not continuous. You know that it's 16 frames or 20. And I will end with this thought, and I will actually come back to the point which you are perhaps trying to indicate. There is a very famous art picture, very famous you'll find, where it is a sketch of a hand with a pencil sketching itself. Okay, so you look at the stars in the night far away, and you think about quantum mechanics, and then you ask yourself the same question that what you're asking: is it reality or it is simply a construction of a human mind? Are we writing our own structure? Are we writing our own thought process? That I don't know. It appears scientific so far. I hope that is all right.
Thanks a lot, sir. That was wonderful session. Thank you all for coming and participating in the session. For everyone